2, 1.
Today I'm going to explain how rolling without slipping actually works in reality. So first of all, let's take a look at the experimental apparatus. I have a plastic. So this is a plastic hoop. So it basically means that all the mass is concentrated at the edge. So all the mass is concentrated at the edge, and I have made a ramp. So the angle can be calculated by measuring the length of the plank and also the height of the ramp. Now let's look at the mathematical deduction. So first of all, to draw a free body diagram, so because all the mass is concentrated at the outer edge, so you have a weight, normal force, so there's a component of weight parallel to the ramp, and also there's a friction force. Well, in this case, we're assuming that this hoop is not slipping. Therefore, this friction force is simply a static friction force. Now, let's apply Newton's second law. So apply Newton's second law. First of all, I'm writing that, looking at the free body diagram, I'm going to write mg sine theta, which is, parallel to the ramp minus friction force, which is equals to mass times acceleration. This is simply Newton's second law. And also, let's look at the rotation. Let's apply Newton's second law of rotation. So friction force, in this case, is static friction force, providing a pure rotation. So friction force times the radius r should equals to moment inertia times angular acceleration. Because right now we're assuming that the hoop is not slipping. Therefore, so this moment inertia in this case is simply m times r squared. Now, because we're assuming there's rolling without slipping, therefore the alpha angular acceleration should simply equals to linear acceleration or tangential acceleration divided by radius. So in this case, let's simplify. So the friction force, you can see that both this r is cancelled, r squared is cancelled, r is cancelled, which I get the friction force equals to mass times acceleration. Now let's plug into the initial formula, which I get mg sine theta should equals to 2ma. So mass is also cancelled. So you can see that linear acceleration should equals to g sine theta divided by 2. So that's mathematical deduction. Now let's do a quick data analysis. So in this experiment, I can using a millimeter rule to actually measure the vertical height of the ramp. And also, I can measure the length of the ramp, which is 70.0 centimeter plus or minus 0.1 centimeters. That's my best estimate. And also, I can get sine theta equals to h of L, which is I get these values. So for theoretical acceleration, linear acceleration equals g sine theta divided by 2. That's based upon my previous assumptions that we're assuming that the hoop is not slipping. Therefore, I get a theoretical acceleration roughly equals to 0.53 meter per second squared. So in reality, by using video analysis, so that's my first set of data is 1.60 second plus or minus 0.1 seconds. And also I can using a stopwatch, which read now 0.160 second. So I repeat for 3 times and I calculate the average value, which is 1.62 seconds plus or minus 0.3. This is absolute values in measuring time, which is maximum value minus minimum value divided by 2. I get these values. And finally, in reality, the average time is 1.62 seconds, and plug in uniform accelerated motion, which is length equals 1/2 linear acceleration times time squared, and get a acceleration in reality, which equals to 0.547 meter per second squared. You can see that these two values are very close, less than 5%. You can see, so my model works very well, which proves that physics works.